Bryan Denny began diving in Tasmania when he was just 9 years old. After nearly 40 years, he knew these waters inside and out. Yet in 2021, he was shocked by a strange phenomenon he could not explain. The green beneath the sea had disappeared. All he could see were dark stretches of rock covered by millions of long-spined sea urchins. They crowded across the seafloor so densely that there was almost no room left for anything else to survive. In a short period of time, the entire area had turned into an urchin barren, driving Bryan's catch to its lowest level ever. But Bryan was only witnessing the result of a process that had been unfolding quietly for years. For 2 decades, marine ecologist Scott Ling had been tracking the spread of Centrostephanus rogersii, and after 24 months of experimentation, he discovered a turning point that could rapidly restore these dead underwater areas. But there was still one major problem that neither he nor many other experts had been able to solve. And over the next 2 years, what did Tasmania do to eliminate 20 million of these invasive creatures? First recorded in Tasmania in 1978, the Centrostephanus rogersii sea urchin alarmed scientists when they traced its origins and discovered that it had expanded its range nearly 700 kilometers southward. It did not need to swim or hitch a ride on boats. Millions of larvae were carried south by the warm East Australian current. Even Tasmania's winter waters remained at temperatures suitable for their survival, allowing their numbers to explode rapidly. In just 15 years, the sea urchin population increased by more than 7 million, and by 2017, Scott Ling estimated that their numbers had surpassed 20 million. But the true figure could be even higher. He also pointed to something even more concerning. At depths of 18 to 30 meters, where urchin densities and barrens were increasing the fastest, some of Tasmania's most important ecosystems were located. These were Tasmania's giant kelp forests, where Macrocystis pyrifera can grow from the seafloor almost all the way to the surface, creating a true 3-dimensional underwater forest. Beneath these kelp canopies, abalone, rock lobsters, fish, snails, and countless smaller animals find food, shelter, and places to reproduce. But to Centrostephanus rogersii, the kelp is simply an attractive food source. Thousands of urchins crawl across the reef, using their hard teeth to scrape away both mature kelp and newly emerging shoots. Patches of green are gradually stripped down to bare rock, and those patches eventually connect into vast urchin barrens. Tasmania has lost around 95% of its historically dense giant kelp canopies. Take a moment to think about that number, because marine life is now being forced to crowd into the remaining 5% or disappear. That is why Scott Ling's 24-month experiment became so important. He discovered a way to make kelp forests that seemed dead begin returning at an almost unbelievable speed. We'll come back to that later. But before humans intervened, nature already had predators capable of getting past those spines. In Tasmania, large southern rock lobsters can flip over and eat sea urchins, but the biggest and strongest individuals have become less common in many areas after years of harvesting. Farther north, in New South Wales, eastern blue gropers are even more formidable. In one experiment, they accounted for about 75% of the observed predation on Centrostephanus, and large fish were able to handle fully grown, heavily spined urchins. But in Tasmania, blue gropers are very rare, and without enough predators, the urchin population has only continued to grow. As these urchin barrens began swallowing kelp forests and threatening fishermen's livelihoods, Tasmania was forced to act by removing the urchins from the reefs before they could destroy even more kelp. At first, Centrostephanus was harvested for its roe and sold as food. But that approach did not solve the problem. The market only wanted large urchins with plenty of roe, while smaller ones were left behind to keep growing, reproducing, and scraping away young kelp. So Tasmania shifted to a more aggressive strategy: take-all harvesting. In May 2023, that strategy was tested at Fortescue Bay. Along roughly 5 kilometers of coastline, surveys estimated there were nearly 230,000 Centrostephanus, equal to about 70 metric tons of biomass, while different forms of barren had already affected around 37% of the reefs surveyed. Over 5 days, teams of divers descended onto the rocky reefs, using tools to pry the long-spined urchins from crevices, pack them into large mesh bags, and haul them to the surface. After 173 hours of underwater work, they had removed about 73,000 urchins, nearly 1/3 of the original estimated population. On the deck, heavy mesh bags were packed with tens of thousands of black, spiny spheres. Looking at those numbers, it would have been easy to think Fortescue Bay had finally been saved. The battle had only just begun. When scientists returned to survey the seafloor, urchin densities were still too high in many areas. For kelp to have a chance to recover, densities at some sites needed to fall to around 0.2 urchins per square meter. And even after 73,000 urchins had been removed, many areas were still above that threshold. So while removing 73,000 animals sounds like a huge number, it did not mean every part of the reef had reached the level needed for kelp recovery. As long as urchin densities remained too high on even one reef, newly growing kelp would continue to be eaten away. To understand why removing tens of thousands of sea urchins was still not enough to bring the kelp forest back immediately, we have to return to Scott Ling's crucial experiment. He selected 6 small urchin barren patches off Tasmania's east coast. 3 were left untouched, while nearly all Centrostephanus rogersi were removed from the other 3. During the first treatment, about 169 urchins were taken out of the experimental patches. Ling then planted no kelp, seeded no algae, and introduced no additional animals. He simply removed what had been continuously grazing the seafloor bare, then waited to see what nature would do. The response began almost immediately. Within about a month, filamentous algae and young seaweeds, less than 20 millimeters tall, began covering the rocks that the urchins had previously scraped bare. Then came Eclonia, radiata, and Philospora commosa. Small kelp plants began growing upward, becoming denser, and gradually forming a new canopy. After about 15 months, canopy cover had exceeded 50% enough for the area to return to a macroalgae-dominated state. By around 24 months, the algal community structure in the urchin removal patches was no longer clearly different from the healthy kelp forests nearby. Meanwhile, the 3 patches where Centrostephanus remained continued to be bare barrens. The most remarkable part was that the forest essentially rebuilt itself. Ling did not need to plant kelp one by one. Once the grazing pressure disappeared, spores from the surrounding kelp forests quickly reclaimed the open space. Throughout the experiment, fewer than 10 additional urchins had to be removed after moving back into the treated areas. Was the experiment successful? Yes, very successful. But that same experiment also revealed a much bigger challenge. The problem was that Beachena was almost an ideal situation. The patches were very small, surrounded by healthy kelp forests, spores were always nearby, and the urchins had been removed almost completely. In the real ocean, a barren can stretch for hundreds of meters, with urchins hiding deep inside rocky crevices, living across different depths, and continuing to return. More importantly, if a barren has already grown too large, the parent kelp forests that supply spores may simply be too far away. So Ling's experiment succeeded, but it succeeded as proof that recovery is possible, not as a formula that can be copied exactly across all of Tasmania. But killing the urchins only clears the ground. It does not automatically create a new forest. In small barrens located next to healthy kelp forests, spores can still drift in and cover the bare rock with new growth within just a few years. But in places where giant kelp has disappeared across much larger areas, the natural supply of new spores is no longer enough. In the late 1990s, Tasmania still had more than 400 hectares of Macrocystis pyrifera forest visible from the sea surface. By 2015, that area had fallen to less than 10 hectares. So while divers continued removing thousands of Centrostephanus from the reefs, a team of scientists began doing the opposite, creating a new generation of kelp. Researchers collected reproductive material from about 50 surviving giant kelp plants across 6 forests in eastern and southern Tasmania, then cultivated different kelp strains in the laboratory as a kind of seed bank. But they were not simply looking for the fastest growing plants. They exposed these strains to different temperatures to see which ones might survive in the oceans of the future. At 12 degrees Celsius and 16 degrees Celsius, most grew well. As temperatures rose, many strains weakened or died, but about 10% continued to survive and grow well. Some even survived in hotter trials. These individuals became candidates for reintroduction into the ocean. Then, instead of dragging giant kelp plants several meters long down to the seafloor, scientists grew extremely small juvenile kelp and attached them to ropes or other carriers secured directly to the rocks. From these tiny, almost unnoticeable strands, giant kelp can grow rapidly if conditions are right, with long stems rising like underwater tree trunks before spreading their canopies toward the surface. But even here, nature continued to show that restoration is not simple. At one test site, the young kelp grew well. At another, they nearly disappeared when sediment and competing algae covered the surface during the summer. The lesson was clear. Placing kelp on the rocks does not mean a forest will appear. In October 2022, IMAS scaled the work up to about 7,000 square meters, testing whether it could move beyond planting small patches and begin rebuilding an actual forest. By 2024, the restoration effort had expanded into a program worth about AUD 3.5 million, with plans to work at 20 sites covering a total target area of around 10 hectares. And this time, they were no longer simply talking about planting kelp. They began talking about restoring the entire reef. One team removes urchins. Another places young giant kelp on the seafloor. Competing algae are controlled. Rock lobsters are being considered as a way to increase predation pressure on urchins in the future. Everything has to work together, because if you only kill the urchins, there may no longer be enough kelp left to return. And if you only plant kelp, the urchins may simply eat the entire new generation. When harvesting sea urchins purely to destroy them became too expensive, Tasmania chose a more practical approach. Turn the very species destroying the kelp forests into a valuable food product. Inside Centrostephanus rogersii are the gonads, commonly known as uni, a seafood delicacy eaten in many parts of the world. Instead of simply paying people to kill the urchins, divers began bringing them ashore, sending them to processing facilities, extracting the uni, and selling it to restaurants. According to fisheries scientist John Keane, Tasmania has been harvesting around 500 metric tons of centro each year, equivalent to more than 1 million urchins removed from the reefs. But the work is far from easy. Divers have to descend to the seafloor, use their hands and tools to pry each spiny ball from cracks in the rocks, pack them into mesh bags, and haul tens of kilograms back to the surface. The problem is that the market is only profitable when the urchins are large enough and contain plenty of uni. Smaller individuals, or areas where urchin densities are low, are often not worth the time and fuel required for divers to harvest them. So Tasmania had to use subsidies to push the fishery into the places where the ecosystem needed it most. The program began at around A0.75 per kilogram and 2.016, then increased depending on the area. By 2.026, support in some regions had reached it around A2.5 per kilogram. The government even brought restaurants into the effort. Beginning in June 2026, eligible businesses could receive reimbursements of up to $1.500 for trialing Tasmania's long-spined sea urchin on their menus. Normally, overfishing is something conservationists try to prevent, but here, intentional overharvesting became the goal. Not to wipe out Centrostephanus entirely, but to reduce their density to a level where they could no longer turn kelp forests into barrens. But eating the urchins created another problem. Uni makes up only about 5–15% of the animal's total weight. After the edible portion is removed, most of the body remains, the hard shell, spines, jaws, and other tissues. With around 500 metric tons of urchins harvested each year, that could theoretically leave hundreds of tons of waste material behind. Instead of throwing it away, researchers at the University of Tasmania experimented with drying the urchins, grinding them into powder, and returning that material to agricultural soils. Analysis showed that it contains high levels of calcium and magnesium, along with phosphorus and other minerals. In tomato trials, centro powder showed no signs of toxicity and was able to improve some soil properties, although it could not completely replace conventional fertilizer. Australians have shown something very clearly across many ecological restoration projects. When one solution is not enough, they keep trying another. Removing urchins by hand with divers has worked, but with millions of them spread across the seafloor, Tasmania knows that human labor alone cannot keep up. So they began testing more aggressive methods. One of them is quicklime. The material is taken down to the seafloor and applied directly to areas containing centro. In trials, urchin mortality exceeded 96% and in some cases reached 100%. It seemed they had found the perfect weapon. But a problem appeared immediately. Quicklime cannot tell which species should be killed. Blacklip abalone can also die, even though this is one of the very species Tasmania is trying to protect from sea urchins. So, a method that is extremely effective at killing Centro also risks damaging the very ecosystem people are trying to save. Quicklime is better suited to barrens where abalone have already largely disappeared, rather than something that can be used everywhere. And Australians did not stop there. If chemicals were not precise enough, they decided to send machines underwater. IMAS, the Australian Centre for Field Robotics, and Hulbot developed a prototype robot equipped with cameras and computer vision to identify Centro automatically, hold its position in moving water, approach its target, and then drill through the urchin's shell to kill it directly on the reef. An even more ambitious idea is to deploy multiple robots at the same time. They could map the seafloor, share the locations of individual urchins, and systematically sweep through areas that need treatment. Most importantly, the robots could operate at night when Centro crawl out of rocky crevices to feed and become easier to detect. By 2025, Tasmania had also provided around $31,080 in funding for a new underwater drone project testing tools such as a stabber, thrasher, and hook. After years of harvesting and culling Centro, Tasmania still has not been able to eliminate the population of more than 20 million urchins living across its east coast reefs. In reality, the goal is no longer to remove every single one, but to push urchin densities low enough for kelp forests to reclaim the seafloor on their own. And in some places, that strategy is already producing visible results. At Wineglass Bay, one culling campaign killed 15,166 urchins in just 3 days. Average Centro density fell from about 1.51 urchins per square meter to just 0.13 per square meter after 1 year, a decline of more than 90%. Once the grazing pressure disappeared, rocks that had been scraped bare began to be covered by algae again. In one area monitored for longer, survey footage after about 5 years showed that the kelp canopy had fully recovered, although abalone had not yet clearly returned. And this is no longer just a small experiment. The Tasmanian government now confirms that across 9 priority areas being monitored, Centro populations have begun declining in 3 of them, where harvesting has reached about 10% of the population. More importantly, kelp has started growing back in those same areas. They still have not won. Millions of urchins remain across deeper reefs, and about 15% of Tasmania's east coast reef area is still recorded as barren. And worse, humans can remove sea urchins from the ocean, but they cannot stop the ocean itself from continuing to deliver new generations. Offshore, the East Australian current keeps flowing south, carrying warm water and Centro larvae so tiny they are almost impossible to see with the naked eye. That is what makes this battle completely different from eradicating an invasive species on an isolated island. Adult urchins do not need to crawl hundreds of kilometers. When they reproduce, their eggs are fertilized in the ocean, producing tiny larvae that drift freely through the water column. For weeks, ocean currents can carry them south. As Tasmania's winter waters increasingly rise above about 12 degrees Celsius, conditions become more favorable for those larvae to survive, settle onto the reef, and establish new populations. This process has helped Centro expand its range roughly 700 kilometers southward over several decades. And by 2026, a new warning sign had appeared. A Centro measuring about 127 millimeters was found between Port Davey and Low Rocky Point, becoming one of the westernmost records in Tasmania. A single urchin cannot create a barren, but its presence shows that the species range is still shifting, even as millions of individuals are being removed in the east. That is why scientists still cannot declare victory. Models based on past rates of barren expansion have warned that if the trend continues without strong enough control, around half of eastern Tasmania's reef area could shift into a barren state by the end of the 2020s. This is a projection, not a guaranteed outcome, and current control programs are specifically trying to change that trajectory. But if they fail, kelp will not be the only thing lost. So will habitat for abalone, rock lobsters, fish, and hundreds of bottom-dwelling species, along with part of the ecological structure of the Great Southern Reef. Let's return to the image that opened this story. Bryan Denny looking down at the seafloor and seeing long-spined black balls taking over the kelp forest he had known for decades. It is easy to see Centro as an invader, but the truth is more complicated. They are not trying to take over Tasmania. They are simply reproducing, feeding, and taking advantage of the new conditions being created by a warmer ocean. As seawater changes, kelp weakens, Centro larvae drift south with the currents, while their predators do not always keep pace. And little by little, green reefs are replaced by barrens. So Centro is not the only cause of this crisis. It is one of the clearest signs that Tasmania's marine ecosystem is shifting into an entirely different state. But in Tasmania, any response has to happen fast enough, strongly enough, and in the right places before the ocean changes faster than people can react. So what do you think? If saving an underwater forest requires removing millions of sea urchins, should humans keep intervening, or are we trying to preserve an ecosystem that climate change has already begun to alter forever? Share your thoughts in the comments. If you enjoy true stories about how people and animals are changing the fate of nature, subscribe to the channel. And don't go anywhere, because the next video will take us somewhere else, where bringing back just one animal species caused an entire ecosystem to begin changing in ways no one expected.